Good afternoon. Well, we're up to about page 8 in Nonlinear Electromechanical Effects and Applications. G.A. Maugin from World Scientific, from series edited by RKTCA. And, we're up to about page 8, and I thought I'd skip ahead a bit and read some of the descriptive text that help describe some of the things and help establish some definitions that will make it so that the vocabulary and its expansion will contain sufficient words, would have enough detail in their context that, according to the theory of types in our vocabulary of our grammar, that it's possible to establish all matters of logical relation of things that make sense. For example, on page 11, section E, singular surfaces. Global forms of balance laws are of special interest since they contain potentially both the local balance equations in the bulk of the continuum and local surface equations at singular surfaces or at a limiting surface boundary. The consideration of singular surfaces comes naturally in the picture. Let a material volume V be cut by a discontinuity surface, sigma t. The latter separates two regions, V plus, limited by sigma plus, and delta V plus and V minus, limited by sigma tilde and dV tilde, or minus. So here he starts to describe essentially a region with a boundary and a separation. And as we talk about the consideration of the particulars of boundaries, that after Brentano, who is a famous logician and who established much of the thinking and the comprehensive thinking about boundaries, who was burned at the stake by the Spanish Inquisition, that boundaries help establish what goes on in terms of the singularities when there's the sense that the tangent to a circle or two circles in their tangency, or as of two spirals where they connect or at their tangency, basically reflects a boundary, yet at the same time that the shortest distance between the centers of those two circles is orthogonal to the boundary and goes right across it. So in this consideration of singular surfaces, it goes and described in terms of an absolute speed of propagation in the unit normal, where normal often means orthogonal to a milieu or the normal or flat. And then he starts describing about the generalized Green-Gauss theorem, where Green, as was mentioned in an earlier discussion, is most famous for gradient descent and also for Stokes theorems, which are important in terms of laminar flow, fluid flow, and various other considerations where Stokes theorems, after Green, arrive at what are very particular considerations of how things can be solved with linear equations when really they have nonlinear establishments. So he writes that the Green-Gauss theorem, generalized, is that the integral of where the range of integration or the surface of integration is dv dot minus sigma t. That he's established that the surface of integration really is usually in terms of not something that's a differential itself. And so he's kind of embodying in his notation that there's a reflection on infinitesimals of quantity a dot ri, or rather, a dot n dA, where then it's the integral over the differential of a. Here that the integral notation is a S for summary bar. That's from Leibniz's notation from the invention of the integral calculus. And that D for differential is again Leibniz's notation. When we talk about Newton's notation, that was with like F dot, or what's called a fluent notation, or with his fluents, which are the units, and fluxions, which are the infinitesimals. Here for Leibniz is that his summation bar is a fluent, and the fluxion is the differential, where the differential or the infinitesimal or the standard infinitesimal or the fluxion are all the same notion of an instantaneous or infinitesimal rate with respect to what's almost always with regards to some other quantity, that it expresses the ratio of these things, that in terms of what results in the quadrature, which is a computation of area, or mensuration, which is a computation of measure, or area, that the integral, which is the computation of area between two surfaces or in an integrable region, that it results that the integral of the differential is a finite quantity that has a perfect solution according to the integral calculus of the computation of a given real function, the area underneath it, its integral, given its bounds of integration and these types of things, the boundaries we were just discussing. And thus the theorem is that this first quantity mentioned is this equal to the integral of v minus sigma t, again, kind of funny, with a del dot a, and this is, again, when we talk about Green and Stokes, we have to consider div, grad, and curl, and del, or nabla, the operator, dot a dv, plus integral over sigma t of the outside brackets of a, and that would represent in this box notation, I'm not quite sure what, dot n dA, and so that containing the inner product or the dot product is as of some outer sum dot the n, which is just a real variable, and so that results in basically a reflection back from the inner and outer sums, or products rather, what we were talking about before. That here, that is what's to express the generalized Green-Gauss theorem, where Green is, as we mentioned, this fellow, and then Gauss is, after Euler, kind of considered really the biggest proponent of what's called the complex analysis. And then what with regards to that, there's Euler's identity, which is established about the e to the I pi equals -1, or e to the I pi plus 1 equals 0, or whatever it is, that then that really results just kind of a convention, or about picking a principal branch, when just like a square root has two square roots, the positive and the -1, that one of those is called the principal root. That in terms of the complex analysis, what they get talking about is really what is in terms of complex analysis is not so much all the possible things that it could be, but instead is about a principal branch, thus that it's possible to result that there's some simple, what are called addition formula, where you have something that's a complex value or number, and by its exponents or what, you can add those together and compute the product by computing the sum. So when we talk about addition formula and complex analysis and Gauss and why those things are like so, it's kind of along the lines of that. It's really just a convention about an addition formula. And so then when we get back to the roots of unity and roots and powers and these types of things, that's something as familiar notation is that when you multiply two exponentiated terms together, you can compute their product by summing those exponents with respect to logarithm, and Jean Napier, Napier, a Scottish fellow who invented logarithm and first made the great tables of logarithms, that's really what is about the utility of these kinds of numerical methods, as well as the solutions according to identities that make for addition formula, that it works out very easily and well, that then these things very much simplify computation. So when we get talking about the utility of these things, then when we start talking about in these linear methods and when they have to make use of approximations like a small angle approximation or what's called linearization, about where, for example, when we think in the infinitesimal and the vanishing, that sine x is the same as x. And that's used to basically make an approximation that, again, for some of these things that are like addition formula, the idea is that they're perfect. But then for some of these other ideas where they're addition formula, it's after there are approximations. So the idea is that they're neglected terms, as what they're called, that it's able to define under this boundary that what is the quantity is vanishing or zero with respect to the continuum and either side of zero, as we were talking about. So that results that is how these things are when they're well defined in their behavior, or what's called well behaved, it's possible to get a result that is to first order terms exact. Then that as there are higher order terms, or when something's really expressed by an infinite series of things, but that the first few terms contain most of the content of the value, that it gets to, just like when we're integrating something and we can kind of break it down into boxes like Riemann sums, and we can start computing finite differences, that those add up, but it's only ever perfect when we get to something where it adds up for all the higher order terms. And so that's when we get to something like the theorems of the integral calculus, that it's possible to compute according to Riemann sums, or what's called Lebesgue or Lebesgue-Stieltjes, that these integrals, as they're so well defined, add up for mensuration and the computation of area, which is often enough quadrature, but that's something for its own discussion in terms of the quadrature and the quadratic sieve, or sieve, that the formulas are only perfect and exact in their infinite evaluation. And the power and strength of the integral calculus is that according to the power law and the fundamental theorems of the calculus, that it's possible to result at what are perfect quantities only in the evaluation of these infinite series, and that the strength of numerical methods and approximation is that via computing only a few terms, you get a very, very close result. And the idea of these error terms of these approximations is that every approximation has an error term associated with it. And the idea is that goes to zero as you crunch out enough terms that result the initial sequence of what is an infinite sequence. And so these kinds of things are where the methods have been built up about these well-defined and well-behaved formulas. And well-behaved is a usual kind of definition of boundary up to boundaries and after initial values, that the computation of a value doesn't have asymptotes and ends up being a finite value. That the discussion of what these constraints are is what results for all our matters of differential equations where they do and don't apply. So here for this generalized Green-Gauss theorem, he's kind of written some shorthand in this notation after Leibniz's notation, and engaging the raw differential, which is just a differential by itself and not a differential as a ratio with the other differential, which is the instantaneous rate of change and known as the derivative. That when we're taking the differential by itself and not under the integral bar or over another differential, that it then results that we need to think of that as a notation about not just their ratio, but also under the conditions where it's well behaved, that it's well defined, that those infinitesimals either have zero as their analytical character, or that they add up, as these terms of integration seem to suggest. He goes on that the second theorem of importance expresses the time derivative of a volume integral. And so here, when you're taking a time derivative, that's basically taking the derivative with respect to t, this universal time that is the parameter of all real value formulas. And he mentions Thomas, 1949. For v plus bounded by dv plus and sigma t, we have d to the dt, or d slash dt, d over dt, taking the derivative with respect to t, of the integral over the volume plus psi dr equals, so it's integrating over r for the surface v, that it equals. He's able to take the derivative with respect to time as its partial inside that formula plus del dot v psi dr, and then he takes the inner product to the other side. So basically, again, he's figured out that he can take some terms that, with both sides of it, keep together this addition about the continuity conditions being on either side of zero, and he's able to use something that's a product in product terms, or is in terms of infinite sums, into addition, and to leave it in terms of that where this does or doesn't have any terms of error, the error term after any approximation ends up being that it's all contained as a convention in the notation, and that equals the same first term plus the integral over the partial derivative with respect to v, and minus this integral of sigma t psi plus v and dA. Now, what that gets into is that there's the derivative and the partial derivative are two different things. Now, the derivative is the derivative or the instantaneous rate of change in time with respect to the change of the entire variable, whereas the partial derivative is holding the other differences constant. And so that basically is kind of along the lines of considering that thus what will result as the differential or the derivative is, as with the other terms, held constant. And where, for example, they're related, that there's an evolution or a motion according to more than just the term that's used for partial differentiation, then it's possible to consider why there are conditions that make that this has to be very carefully defined to be constrained, to be well behaved, thus that it results, it gets a finite quantity and doesn't blow up in higher order terms or result in nonsensical values or these kinds of things. So that's an example of one of these generalized Green-Gauss theorems, and it helps detail some of the considerations of what are the conventions that basically hide what are the worries of what would be the matters where after boundaries or initial values in initial value problems and boundary value problems in what's called differential analysis, and as to why very small changes could result in very large differences, that then it's possible then to write such an equation on one line according to these variables have built up all this context in them together. Thus that looking at one of them or a few of them by themselves is kind of inscrutable, yet that each is its own linear declaration, that what's necessary is to result that the methods that go into them, whether they're perfect, like the integral calculus, or with an error term, like a numerical method that makes an approximation, that these are these kinds of things relevant to understanding what's going on. So in section A of 1.2, under balance laws, he says mechanical forces. According to Cauchy, the mechanical force T sub j, the stress vector, exerted per unit of surface on a regular surface of unit normal n in the configuration, remember the first diagram, kt, can be expressed as a linear expression, T sub j equals n sub I T sub ij, where T sub ij is the Cauchy stress tensor. So he's described that the stress vector, according to this normal, can be written in these terms, linear, meaning that they have linear roots, and also that there's many other formulas you can call linear by the fact that it results that you can compute to draw a line on them, is the Cauchy stress tensor. Forces F equals series Fi can also be applied for unit mass of the bulk of the material. And see, here he's describing, kind of like when we talked about the test particle or an infinitesimal region, that the unit mass of the bulk of material basically is when you consider the thing as a whole. And that this whole encompasses the entire thing and it makes a unit. And so when you have something that's multiplied by 1, you can talk about it being standardized and normalized because 1 is the multiplicative identity. And so if it was any less than that, when you multiply those, it gets smaller. But it's any more than that when you multiply those, taking their square and so on, what I mean by multiplying those things together with themselves, that it gets larger. And so that's why when we talk about the standardization and normalization of variables, it's after you've taken what would ever be its large finite extent, dividing that by its length, you end up with something that's 1. And so then when we talk about this quadrature, like I'm going to take the square or the root of what's larger and smaller than it, then those get smaller and vanish when it's less, and they get larger and blow up when it's more. And so that's why we talk about sometimes you hear that there's something is the unit of something, that's really kind of what's going on with it in terms of a regular surface. And here that the surface has more than one unit in it, but the unit normal is exactly a vector, exactly one high. And then in terms of addition, it's ignored, because what happens is there's multiplication about values lesser or greater than it. And that's when we get to talking about things that are like the triangle inequality, or what's called the Cauchy-Schwarz inequality. It's called the triangle inequality, and basically it sets it up that when you have orthonormal terms and the so you have like a unit x and unit y, and you draw the triangle of them, that in the quadrature as of the square, that the triangle inequality always establishes that according to the metric in the distance, that it establishes a condition and a criterion that something is, for example, vanishing. So you can ascribe to it according to this formalization after the methods of the numerical methods, including approximations, but more about the analytical methods, the result real analysis, that there's the triangle inequality. And that these kinds of things are very useful. And in fact, if there's one thing that is the rule in most things that are methods of quadrature used in physics, it's a triangle inequality. So we shall assume that the latter have no electric origin, e.g. they are gravity forces. And so here, that's when we talk about things that are forces. We basically have forces equals mass times acceleration. And another way to look at that is that force over acceleration equals mass, or what we can do with in terms of algebra, that those are quantities, and when they're linear and first order quantities and all self-contained, that it's totally free to cancel either above or below a divisor bar, or divide both sides of the equation by a constant or quantity or variable, or multiply both sides, or add or subtract to both sides of the equation, whatever is equal. But then when we have that there are considerations after the numerical methods, that it's only carefully well-defined and well-behaved when the values are in their addition formula, or according to their products, well-behaved about the numerical methods that are implicit in the notation and implicit in the convention, that's why there gets into the reasons that algebra is sometimes allowed, and the other times there's a framework in place where it would break. So these are, again, just your regular concerns of any kind of what's called manipulation of terms, or when you rewrite formulas and systems of equations in terms of other formulas and systems of equations, that what's relevant is almost always is algebra and the ability to manipulate terms in terms of their telescoping expansion for the infinite series. But in terms of their what's linear about them, that you can add and divide either side, and that's how these things work. So after mechanical forces, then he says in section B, electric forces. In a dielectric solid, in the quasi-electrostatic approximation, the falling force and couple act upon the material as a result of it being electrically polarized in an electric field. So a force is an impulse. It is basically a microscopic or infinitesimal push in exactly one direction. Whereas a couple is basically as how things are connected. And so then that gets into notions like static and dynamic friction, any kind of interface or boundary between two things. That the force is P dot del E, the electric field, and the coupling is E electric field cross P. And so the cross operator is similar as we were talking about the inner and outer or scalar and vector products before, that the cross product is a very particular product, and it's defined in terms of orthonormal vector bases, and it only pretty much exists in dimensions 3 and 7, which is a very particular thing, because it's not so much generalized to all the other dimensions. What with respect to something like a dot product is always reducing, and that an outer or vector or wedge product sometimes exists in terms of the generalized of these things. That in terms of the cross product, it exists for dimensions 3 and 7, which makes it very convenient that then in terms of how Green and Stokes theorems are derived in terms of div, grad, and curl, that the cross product and the what's called the right-hand rule, which is a convention as to where when you take the product of using a cross product to compute the product of rotations, that it ends up thumbs up, that as a purely arbitrary choice, that is how then it results that in terms of P dot del and of times E and E cross P, that they basically represent complementary things, just like we were talking about the unit normal being orthogonal as a matter of the between the boundaries, that the shortest distance, that here the force and couple are basically complementary things. And so that in that sense, they reflect both the transit and what happens when something goes through, and as well the inertial moment or what, things that wait. And when we talk about Newton and his laws, and for example, that what is in motion stays in motion, what is at rest stays at rest, it's a similar kind of thing, that they use complementary qualities, because you can't really ever say that something is really at rest or really in motion in terms of that these are in their locales. That it's not really, when we talk about the point, local, global, and total, that these are very much in terms of our local measurements, that from as close as we can get without it filling our entire view, that all we can see is that these things occur. So anyways, I spent a few minutes talking about a half of page 11 and half of most of page 12. And so we'll get back into this some more later, talking about, what's here about the balance laws again, where balance laws basically are what results in these complements, that the continuity conditions are held up, so that then you can say that these things have, in terms of algebra, how they can cancel, and it is possible to compute with them. All right, here's some other books I was looking at, and these are pretty high-level books, and they're produced by a mark called Dover Press. Now, what Dover is they get all these great, seminal, important books in physics and mathematics and engineering, and they reprint them. So, for example, this Dover edition of multiple beam interferometry of surfaces and films, after T.S. Tolansky of the University of London, that Dover Publications has reprinted this, where it was originally from Oxford University Press. And what they do is they make it possible for what these original editions, as they've maybe gone out of print, that the Dover editions really reflect that there's all kinds of important works that Dover reprints. And so when it comes to marks and publishers, there's that one of the best ways to build a library. For example, this was originally $3 in 1970 money. That it results in these kinds of considerations going on in interferometry, which is like all this stuff to do with quantum theory, about how two waves have constructive and destructive interference and this type of thing. That these kinds of books really help reflect that it's possible to acquire quite a bit of a library in terms of what works up linear functions, then in terms of stuff like sine squared and 1/2 delta. Here may be the impulse function instead of the Kronecker delta. And then it results in as to why it's possible to work up and build out why in these wave formulas and these considerations, how things are built. And he talks about Fizeau, who's pretty great. And we'll talk about Fresnel at some point. He's pretty great. And this other book is called Dynamic Light Scattering with Applications to Chemistry, Biology, and Physics. And again, it's Dover reprint, originally a few dollars. In 1976 money or 2000 money, that helps describe that in the nearly quarter century since this book was first published, dynamic light scattering techniques have become increasingly sophisticated, and their applications have proliferated, encompassing many diverse areas of science and technology. And so similarly, this Hermann Wiles, the continuum of critical analysis of the foundation of analysis, which really is kind of one of the important things when we talk about real analysis and the formalization of the integral calculus and its perfect results after the original sort of works of Archimedes, and since the ancient Greeks was called methods of exhaustion, and then later to much later to Newton and Leibniz, and the integral calculus is after geometry, building things in a numerical setting of real numbers and spaces of real numbers, and Bernard Riemann and Lebesgue and Stieltjes and so on. That Hermann Weyl and the discussion of the continuum is a pretty important thing that comes about in terms of the discussion of the linear continuum and making it formal and rigorous so that the reasoning about it can make sense without it becoming either paradoxical or nonsensical. And so Weyl's book there is something from a Dover reprint that it contains much interesting background analysis of something like that. Then with regards to something like Weyl's view of the linear continuum and something like Brouwer's and somebody like Giuseppe Piano's and somebody like Eudoxus and Dedekind and Cauchy, or Hardy and his real numbers, or the points of geometry and how they're the same thing as real numbers, and what it means to have a continuum and what it means to divide that up into infinitesimals, which are kind of in the reverse or inverse or reciprocal of an infinity and infinitesimal. That the study of the foundation of the continuum is a very fundamental thing, and that's when we get to start talking about foundations, the foundations of mathematics. This is where the foundations of mathematics is basically the entire axiomatic description, or lack thereof, of what results the objects of mathematics. And there's much to be said about that with regard to Plato and the Platonic ideals of that mathematics and logic exists, and or as it was given to us, that we discover it. And in this manner, much to be said then is for axiomatics, or the declarations to follow, like Euclid's axioms of geometry, or an axiomaless geometry just from points and spaces. That what so results will be more about the formalization of the foundations of mathematics, and later also how relevant that becomes in terms of the foundations or the fundamental in physics, where physics today is about relativity and quantum mechanics, which is a continuum mechanics, and right in the middle of there somewhere, and science yet isn't quite sure where, there's gravity. And so when we talk about the foundations of physics and the foundations of mathematics to be discovered, it's possible to rationalize and realize how they arrive as from the same very thing. It's accessible to anybody as a simple matter of reason. Well, all right then, that's this Saturday afternoon's words, and I shall so hope you have a great day, and that we'll read a few more pages with some context applied some other day. So long.